Thank you, Professor, for the kind introduction. So this work is about what? Okay. This work is about.
Wait, Carolina, wait 1 second.
Wait.
Because we are not able to listen you.
Wait.
Okay.
Yeah, try now. No.
Now?
Yes.
Yes. Can I start?
Yes. Yes, you can.
Okay. Thank you for the kind introduction. This work is about the pure torsion effects on bioinspired gyroid lattices. Oh, wait. Wait a bit. Okay. Okay. So let's start talking about bioinspired structures. Among them, we have lattice one, which are quite interesting due to their high mechanical performances compared to high surface to ratio. And among them, TPMS, so triply periodic minimal surfaces, has emerged due to their smooth and continuous geometry that avoids the stress concentration due to sharp junctions. And among TPMS are famous the Gyroid one due to their high mechanical properties and and to their inherent self-supporting structure, which is quite useful because lattice structures are usually 3D printed.
It's forwarding by phone.
What?
No, it's okay.
Okay. That are produced through 3D printing, so it's quite useful. And despite they have been extensively studied under Mod 1 and quasi-static compression, there are quite only few papers about pure torsion and Mod 3. And so it's quite interesting to study it. And another interesting bioinspired structure is the Bulligan one. It has been extensively studied, especially for composites, since it's layered structures, but there are only few info about structures that combines the characteristics of lattice structures and Bulligan. So the aim of this work is to investigate the torsional performance of gyroid-based structures inspired by Bulligan architectures. So this is the workflow of this presentation. I will first show you the Bioinspired design that we carried out. Then I will show you the design of experiments that we developed, and we will go toward the conclusions. So let's talk first about the design. Here I'm showing the reference specimen. It has a cylindrical shape, and we shift toward a radial patterning, imposing two different relative density gradients. The first one can be seen in the A section. Varying the wall thickness, we imposed this constant relative density equal to 0.4 in the constant lattice region, as you can see in the right part of the slides. And then in order to avoid the crack formation in correspondence of the interface of the head grips and of the constant lattice part, we have a gradient zone in which, again, varying the wall thickness, we have a gradient of relative density from 0.4 to 0.6. And this is a layered structures. So looking at the specimen in the right part of the slides, we have 12 layers of the A section that can we see. Then we applied to the reference specimen the so-called Bulligan effect. As a Bulligan structure is a layered structure in which each layer is rotated with respect to the previous one, here we rotated each layer with respect to the base of an angle beta, which is function of z, which is verso parallel to the 8 of the specimen. But since beta is a function, the question was which kind of function should it be? And we came back looking in nature, and we found that for some specific mantis shrimps, in which the club is made of a Bulligan of fibers and it has to withstand to high cycle loads, we have seen that the pitch length of this Bulligan varies according to a function that can be approximated to a parabol or a second order degree polynomial. So we impose beta as a parabol, a second order degree polynomial, and we developed 4 designs. The first one, the green one, it's the easiest one. It's the degenerate condition of a parabol, which means constant variation of beta, which means beta as a linear function. Can be seen both in the graph in the upper part of the slide and the geometry in green in the bottom part of the slide. And then the other 3 geometries that have been developed have been chosen in function of the position of the vertex of the parabol. The blue one, in which the vertex is in the middle of the specimen, and the red ones in which the vertex of the parabol is in the upper and in the bottom part of the specimen. Then for all these 4 configurations, we varied alpha. What's alpha? Let's look on the sign on the left part of the slide. Alpha is the angle in the between of the base plane and looking at the lateral surface of the cylinder, the lateral surface of the cylinder, the angle that forms each cell due to the rotation with the base plane. And varying alpha, it's possible to vary the rotation of the vertex in each one of the configuration that I showed you before. So what we did is to perform the sign of experiment in order to understand which of this configuration could be could be considered the optimized for quasi-static mechanical performances. So let's talk of the first design of experiment. The first is focused on the degenerate condition of beta, so beta as a linear function. We have 2 vertex positions, -1 and 1, 3 levels of alpha. We decided 10, 20, and 30 degrees, and 3 replicate per each condition. Then we performed pure torsion quasi-static test and extrapolated the most important parameters, so torsional stiffness, ultimate tensile strength, ultimate tensile strain, yield strength, yield strain, fracture strain, and fracture stress. Similarly, for the parabolic designs, we impose 3 vertex positions, so in the middle of the specimen, upper and bottom part. Again, 3 levels of alpha, 10, 20, and 30 degrees, and 3 replicates per each condition. And again, we extrapolated the most important factor after performing pure torsion tests. So let's see the most relevant results. Let's start with linear designs. Here I'm showing the results for torsional stiffness. We can see that we have a statistical significant effect of the angle alpha and the interaction of alpha and the vertex position with the torsional stiffness G. And let's look now at ultimate tensile strength and fracture stress, again, we have the statistical significant effect of angle alpha and the interaction of alpha angle and the vertex position, as is shown from both the ANOVA tables. And in this case, we have a quite good R and R square for both cases, close to 70 and 60%, and from the main effect plots and interaction plots. So now let's shift to parabolic design. Let's talk about the yield stress. Here, we can say that there is a statistically nonlinear effect between the vertex position and the yield stress. And even if we have a quite low R squared, we can say that the factor F are real, even if it's a small effect on the yield stress. So looking at the contour plot, we can say that thanks to the info that we have now, the best condition to improve the yield stress is to choose the condition in which the vertex is in the middle of the specimen. And we can make similar statement for the yield strain, where again the best condition seems to be the one in which the vertex are in the middle of the specimen. So let's go toward the conclusions. So we have demonstrated that for linear designs, if we want to increase, to maximize the torsional stiffness, UTS, and fracture stress, we have to choose a condition in which the angle is equal to 10 degrees, and that for parabolic design, the best condition to maximize yield strain and yield stress is the one in which the vertex position of the parabol is in the middle of the specimen. Of course, we want to check these effects even on metals, because we make this test on nylon 12, and even check the effect of these geometries even for fatigue under mode 3. So thank you all, and if you have some questions, I'm here.